Okay, in this video, I'm going to show you how to build the piston for the Shane Wighton two-cycle gas engine. This piston diameter is 7/16 and it's 450 thousandths tall, so it's very small. But it's made from cast iron, so I've already set my material to gray cast iron. My units are inches, pounds, and seconds, and I'm using ANSI drafting standard. The first thing I want to do is select the top plane. I'm going to sketch a circle and extrude it upwards. And by doing it like this, I'm forcing SolidWorks to give me a front view that mimics the view that's on the blueprint that I'm trying to duplicate. So I'm going to type in 0.4375, and it's going to round up to 2 decimal places because by default my SolidWorks is set up to 2 decimal places, but I'm going to go ahead and change that to 4 so we can see it. And I will add the tolerances for this, but there are a lot of tolerances in all these parts. So to keep the videos short, I'm going to show you how to add 1 or 2 tolerances here and there, but this is something that you're going to have to do on a case-by-case basis. So this first tolerance is a plus nothing minus half a thou. So I set my tolerance and precision to bilateral. I'm going to change my upper and lower tolerances to 4 place decimals, and I'm going to go ahead and change that lower one to match what's on the blueprint. So now I have 7/16 plus or minus half a thou. And that's it. I don't want to add any more features to this. I'm going to extrude it upwards to 450 thousandths. And a lot of students say, well, I have my dimension, my tolerance here. How do I dimension the extrusion? Well, when you double click on a feature, the dimension appears. And then I can modify it. In this case, it was a symmetrical tolerance, 3 decimal places, on the extrusion, or the length. So that's how you add tolerances. For the rest of this part, I'm going to leave the tolerances off. Okay, perfect time to save the part. Okay, next I'm going to complete the internal cut using a revolve. So I'm going to sketch on the front plane, create a new sketch. I'm going to create an infinite length vertical center line. And sketch the geometry, or in this case, half the geometry of what I'm trying to revolve. Let me turn my wireframe on so you can see what I'm doing. So I've got my vertical length center line, and now I'm just sketching half of what I want. And I'm going to use this diameter technique, and it only works with the center line. But I want to select, in this case, this would be the whole diameter, and then the center line, and I've got this radius to diameter option. Add my 45-degree angle. Since this is a drilled hole, the angle here would most likely be 59 degrees or 118 total, depending on the size of the drill or the type of drill that I'm using. But it's not dimensioned on the print, so therefore it's not important, and neither is the chamfer, because that's not here either. So as far as the chamfer size or the countersink size, it doesn't matter. If I dimension the chamfer size, I could do something like this and say, hey, it's 60 thousandths. Or I could control the size of the countersink by giving it a diameter. So if I knew what types of tooling I had, and I said, oh, I have a 3/8 bit, and then I plunged it into the part, now I have a 3/8 countersink. So if it's not specified on the print, typically that chamfer isn't super important. And that's it. There's my profile. And now I'm going to turn my shaded with edges back on, and I'm going to revolve cut this around my center axis. And then I'll do a quick file save. Okay, going back to my isometric view, I'm going to drill a hole straight through the front of the part. So I'm going to sketch a circle on the front plane. I'm going to make sure that my circle is in line with the origin. So I'm going to click the center of the circle, the origin, and click vertical. That keeps it in line. And then I'll give it a distance from bottom to here is 150 thousandths. There we go. Its diameter is 126. And I'll do a through all both cut. Since I'm sketching in the middle, I want to cut outward in both directions. I noticed I goofed on the depth of this hole. It's not 150 thousandths, it's 0.406. So I apologize if you were confused up until this point. But the nice thing about SolidWorks is once it's fixed and you model it correctly, you can make changes very quickly. So looks like our, let's see. So maybe our angle is wrong. Okay, so I just noticed a mistake in how the depth of this hole was dimensioned. The distance of 0.406 was called out next to the diameter, and it said a depth of 0.406. A traditional hole depth is always dimensioned to the end of the body diameter like this. So the depth of this hole is technically 0.31. The way that this author dimensioned this hole is bogus. So please don't ever do it like this. This is what they were trying to accomplish by making sure that the drill point didn't pierce through the piston. So this should have been dimensioned explicitly on the print, and it wasn't. So that's a mistake on their end. So what I'd rather see is this right here, from here to here. Okay, and that's a more appropriate dimension. So whatever this number is looks like it's close to 5/16, and that's what I'm going to change it to. So that would be appropriate for this. Okay, and then on a blueprint, I would absolutely show this dimension, you know, and say, you know, something to the effect of max, you know, max hole depth, or give them the distance from the top of the piston to the bottom there and say, you know, please don't drill any smaller than this amount, or else it'll pierce through the piston. All right, so that mistake was cleared up. And then we have this 1/4 inch scalloped corner that I'm also going to sketch on the front plane. I'm going to draw a circle way out in space, dimension its location per the blueprint. So from the bottom of the piston to here is 0.633. And from the edge, the silhouette edge of the piston to here is going to be 0.046. And then if they're calling out for a 1/4 inch radius, the diameter would be 1/2. So we're going to take this circle and we're going to extrude cut it through all in both directions. Okay, because we're sketching in the front plane, we're going to slice right through the side of the piston. And the reason for this scallop is there's going to be a spark plug here that ignites the gas and air, and the explosion kind of hits this surface and this surface combined, and it helps force the piston down in the direction that it's supposed to be. So there it is. There's our cast iron piston. Going through the steps again, we drew a circle, we hit extrude, we had the internal cut, a couple of mistakes made by the author as far as dimensioning, but were fixed and modified, and the hole drilled straight through from the center. Using Hole Wizard, you could do that. You could do this exact feature, but you'd have to use offset planes and axes in order to do that. And then the last but not least step in this piston was the scalloped edge. And file save and move on to the next part.